Progress on the Saturn Space System program during the period January, February, and March 1961 is divided for this report into 4 categories dealing with the booster or first stage called S1, the S4 or second stage, the S5 or third stage of the Saturn C1 configuration, and facilities and equipment in support of Saturn research and development. The Saturn booster is under development at the George C. Marshall Space Flight Center, Huntsville, Alabama, which exercises overall direction of the entire Saturn program. Due to the vast scope of the program, Marshall has called upon the specialized technical competence of 4 major contractors. Douglas Aircraft Corporation of Santa Monica, California, contractor for the S4. Convair Astronautics Division of General Dynamics at San Diego, California, which is performing work on S5. The Rocketdyne Division of North American Aviation Company at Canoga Park, California, which furnishes the 8 H-1 engines for the Saturn booster. And Pratt & Whitney Division of United Aircraft at West Palm Beach, Florida, which will provide the liquid hydrogen engines for both the S4 and S5. Marshall and its contractors are being supported by hundreds of subcontractor firms and government facilities. S1 development work at Marshall this quarter was highlighted by completion of assembly of the first Saturn flight booster. Begun on May 28, 1960, the booster for SA-1, the initial flight vehicle, had progressed early this year to the point of being declared ready for checkout. On January 16th, the 22-foot diameter, 81-foot-long booster was moved from the assembly area the short distance to Marshall's Quality Division. Here, the stage, which initially will generate 1.3 million pounds of thrust, was to undergo an exhaustive series of mechanical and electrical checkouts. Long before the completed booster arrived, however, Quality Division personnel had been checking out materials, components, subsystems, and systems designated for the vehicle. This Rataflow machine, for example, was used in acceptance testing of all relays and semiconductors. The parts were placed inside and pressurized to several atmospheres in a radioactive gas. Pressure was removed and the parts' surfaces air-washed. With a radiation detector, the amount of gas leakage could be determined and an analysis made of the conductor's hermetic seals. This aptly named SMART machine, its initials stand for Sequential Mechanism for Automatic Recording and Testing, provided a functional test of all the stage's semiconductors. In addition, a printed record of the exact DC parameters of each item was made on IBM punch cards. These records will be most valuable in future Saturn design work. Another among the numerous and thorough component tests which were run by Quality Division took place in this low-pressure room, where every valve in the complex space vehicle was subjected to a precise pressure check. Each assembled Saturn component, such as this main measuring distributor, underwent final acceptance tests prior to installation on the booster. The distributor was functionally checked to verify that each measuring circuit was properly channeled and that resistance values conformed to design specifications. Then, after the SA-1 booster arrived at Quality Division and was positioned in the checkout area, work began on conducting a complete continuity check of the entire electrical system. A pneumatic control system was installed in a room nearby the checkout area. From here, as personnel monitored the operation by means of closed-circuit television, the booster's pneumatic and hydraulic systems, such as those which actuate gimbaling of the 4 outboard engines, could be controlled for testing. After discovery of cracked liquid oxygen domes in the Stage's Rocketdyne H-1 engines, these engines were removed in order to exchange domes and then reinstalled. Now, the SA-1 booster was ready for test division. Assembly of the second, or SA-2 flight booster, which began December 27th of last year, was also progressing this quarter, with clustering of tanks completed. Assembly of a new type booster, designated as SA-D, started March 7th. Using components from structural tests in Structures and Mechanics Division, SA-D is being made for use in dynamic testing. The structural testing program continued during this report period, with testing of this short booster assembly with second stage adapter attached. Due to height limitations imposed by presently available facilities, tanks in the booster test assembly are only 184 inches long as compared to the actual 677. However, these load cylinders positioned at the same points as the booster's 8 engines provide accurate simulation of all static and flight loads. This load maintainer regulates correct pressures of hydraulic fluid to load cylinders. Pressure ratios are kept constant throughout the tests. Test information is transmitted from strain gauges, deflection indicators, and load cells back to data acquisition equipment. The information is stored on tape and then fed into a computer which calculates and tabulates deflection and load data. During this quarter, the current series of static firings of the modified test booster, SAT-1, was successfully concluded. When the series began in December 1960, it was estimated that 6 to 8 firings would be needed. However, test objectives were declared fully satisfied after only 4 firings, on December 2nd, December 20th, January 31st, and February 14th. The January and February firings were for 113 and 110 seconds duration, respectively, each generating approximately 1.3 million pounds of thrust. All 8 engines were fired in each test. Following completion of static testing, the test booster was removed from the stand on March 2nd in order to make way for installation of the first flight booster, SA-1, on March 6th. Static firing of the SA-1 booster is due in mid-April. The test booster was moved to the nearby Tennessee River docks and rolled aboard the Saturn barge in an exercise to gain experience in loading and handling techniques. The barge, named Palaemon, will be used later for transporting Saturn stages from Marshall to the launch site at Cape Canaveral. Carrying the booster, the Palaemon left March 15th on a successful 3-day trial cruise downriver to a point near the Alabama-Tennessee boundary and back, passing through locks of TVA's Wheeler and Wilson dams en route. The test booster will be reinstalled in the static test stand shortly after removal of the SA-1 booster in mid-May for a new series of firings. Build-up of facilities and equipment in support of Saturn research and development continued this quarter. At Marshall, the new dynamic test tower, in which Saturn stages will be excited to simulate flight conditions, neared completion. The SAD booster will be installed in the tower in May and assembly finished there, while the test facility itself is being instrumented. Dynamic tests are scheduled for June. Electrical ground support equipment designed to check out and verify circuits within the Saturn booster was completed this quarter by Marshall's Guidance and Control Division. Shown here as an entire unit, The equipment was later moved to Quality Division, where individual components performed SA-1 booster checkout. This rack, known as the Ground Equipment Test Set, simulates electrical circuits of the booster and thus enables the electrical ground support equipment to be completely qualified prior to mating with the vehicle. The equipment is also used during launch to monitor and sequence countdown operations until liftoff. From Quality Division, the equipment will follow the booster to the static test stand and then on to Cape Canaveral. Saturn launch equipment, consisting of 4 support arms and 4 hold-down arms, are now undergoing checkout tests at Marshall. They will later be installed on the launching pedestal at the Cape. The retractable support arms are shown in this slow-motion sequence, moving to the retract position 62 inches in 0.8 of a second. Retraction allows takeoff clearance for the booster's tail shroud section. The hold-down arms then receive an electrical signal from the support arms to release the booster. At the Cape Canaveral Saturn launch site, the launch pedestal is complete except for addition of the support and hold-down arms and other firing accessories. This torus ring, emplaced in February, will be used for water cooling of the launcher and deflector during vehicle liftoff. The base of the umbilical tower is almost finished. The tower itself will not be erected until after the 3rd Saturn flight vehicle is fired. Construction on the blockhouse is finished. Installation of interior equipment will continue through July. The 310-foot-tall service structure is virtually complete, with installation of platforms accomplished this quarter. The RP-1 fuel storage area and liquid oxygen storage facilities will be ready by May for the first flow tests, in which fuel and LOX will be run to the launch pedestal. This skimming basin will be used for collection of spilled propellants. Nearby the 65-acre launch site, the Saturn barge dock and unloading facility has been completed and is ready to receive the first flight vehicle late this summer. The feasibility of transporting the S-4 stage and possibly the booster piggyback on a C-133 is under study by Douglas Aircraft Company. Wind tunnel testing of this scale model is being done at NASA's Lewis Research Center. Also featured in detail in this quarter's film report is developmental work on the Saturn's 2nd, or S-4 stage, being accomplished by the contractor Douglas Aircraft at its facilities in California. This 1/10 scale model depicts the actual S-4, approximately 41 feet long and 18 feet in diameter, as it will appear upon completion. Plastic cutaways reveal significant portions of vehicle structure, such as engine assembly, and the common bulkhead and oxygen tank. Shown in close-up are the S-4's retro rockets, ullage rockets, and pressurized helium spheres. A full-scale engineering mock-up of one of the stage's 4 liquid hydrogen, liquid oxygen, 17,500-pound thrust engines was received in February from Pratt & Whitney. A varied testing program was a vital part of Douglas development efforts. Insulation testing at its Sacramento facility determined properties of insulation to be used in liquid hydrogen tanks. In this test, the insulation sample is exposed to a liquid hydrogen environment on one side and a high temperature, provided by a hot plate, on the other. The test is run to show heat transfer characteristics of the sample. Other insulation tests consisted of determining the effects of vacuum jacket pressure on liquid hydrogen boil-off rates and heat transfer coefficients with a simulated section of the vehicle tank-to-engine low-pressure fuel ducting. Heat transfer and boil-off rate data were as expected, and an analysis of test results is being accomplished to correlate them with theories on cryogenic pumping at very low pressures. Structural testing included a compression test of an 8-foot diameter, 10-foot long cylinder, which was integrally stiffened with a Saturn S4 waffle pattern. Tests showed that the inner pattern buckling began at an actual compression load of 252,000 pounds. Testing was initiated on a prototype model of the helium heat exchanger, which will heat cold helium gas during flight for pressurization of the liquid oxygen tank. After installation of the heat exchanger on the stand, cold flow tests of liquid hydrogen began to gain experience on the transfer of liquid hydrogen between the storage tank, run tank, and helium heater. Scale model combustion engines for the base heating program were received from Marquardt Corporation and shipped to the Air Force's Arnold Engineering Development Center at Tullahoma, Tennessee for testing. Water slosh tests were conducted at the Santa Monica facility on the 3-foot diameter liquid oxygen slosh test model to find sloshing parameters and to determine optimum design and location of baffles for the liquid oxygen tank. Testing was begun on the 300-gallon cryogenic container in the interim liquid hydrogen test area at Santa Monica. The liquid hydrogen surface level has been successfully recorded using an optical tunnel to photograph a still well interior. Observation of the liquid hydrogen surface via a closed-circuit TV camera looking through a 1-inch plexiglass window in the tank has also been successful. It is expected that liquid level determination to an accuracy of plus or minus 1/8 of an inch may be accomplished using a step-type gauge in conjunction with the TV setup. In addition to its testing program, Douglas continued manufacturing work, including fabrication of special tooling needed for S4. This hemispherical bulkhead weld fixture is now nearing completion. It will be used to weld the 6 hemispherical segments of the forward and aft bulkheads and the inner and outer domes of the common bulkhead. Also in the manufacturing area, a Saturn test tank was constructed to test techniques of installing insulation. The waffle pattern is identical to that employed in the S4 liquid hydrogen tank. Manufacturing progress included milling and forming of the initial tank skins for the actual S4 stage. Milling work was performed in the Santa Monica plant, followed by shipment of components to Douglas's El Segundo facility for the forming operation. As testing and manufacturing proceeded, Douglas augmented its facilities to keep pace with anticipated development. For example, this permanent liquid hydrogen test facility, now under construction at Santa Monica, will enable much larger scale testing of materials. A hydrostatic test tower is being built, also at Santa Monica, to be used for hydrostatic testing of S4 tanks. At the Sacramento facility, the foundation for the 90,000-gallon liquid hydrogen tanks has been constructed, and aluminum tank sections have been received and welded to form hemispherical sections. Modifications to test stand number 1 at Sacramento were started. The stand will be used initially for battleship testing. Modifications include installation of an overhead crane and a new exhaust deflector plate. Looking forward to transportation of the completed S4 to Marshall Space Flight Center, Douglas is now negotiating with shipping concerns for probable movement by barge. At the Marshall Center, fabrication of the first dummy S4 was completed in January, and the stage was mechanically mated to the incomplete SA-2 booster for fitting purposes. Extension of Convair's S5 study contract was authorized this quarter. Pending evaluation, it was decided to delay development contracting. At the Convair plant in San Diego, fabrication of the first dummy S5 stage has been completed. Convair's continuing study, however, is expected to re-emphasize possible Saturn use of the Centaur stage with minimum changes to existing hardware rather than development of a new S5 stage. Convair's dummy stage arrived at the Marshall Center in late January. The S5 was mechanically mated to the dummy S4 stage, which was previously mated to the booster. A dummy payload was then attached to the S5, thus forming the first complete Saturn C1 space vehicle configuration.